Hey Firecats, thanks for logging on and watching this video. Today's video, we are continuing to work with exponential functions. So real quick, I'm going to remind us of our standard form for an exponential function, a times b to the x power. And let's define those variables. When we're writing our own function, a is going to be our initial value or our starting value. Remember that a also tells us the y-intercept, so that should make sense. The y-intercept is our starting point. B is going to tell us how quickly the situation or how quickly exponential growth or exponential decay is happening. So that's going to tell us the rate of the growth or decay. And then our inputs here, our x value, are going to be units of time. And we want to make sure when we're putting in these values that the unit of time matches the unit of time in the rate for the b variable. So I'll explain more about that. Let's jump into some examples. So some helpful things to know before we start. If something is appreciating, it's experiencing growth. If something is depreciating over time, it's experiencing decay. Okay, so let's read our first example. It says a new car is purchased for $17,900. Okay, so I know that right away that's going to be my initial value, my A value. And then it says the value of the car depreciates at 13% per year. So I already know this is decay. And that 13% is the rate that it's decaying every year. And then it says, what will the value of the car be to the nearest cent after 7 years? So that is our time, that's our input. And just to double check, the unit of time does match the rate. The rate is given per year. All right, so let's build our exponential function. Start off with standard form, and then we'll start to fill in some values. Just to say it, there's some interesting stuff about cars and their value over time. I'm not going to go through those, but you can always pause and read through those or read through them on the notes. Okay, so now we need to start filling in our variables. I already know that A is my starting value. This car initially was purchased for $17,900. To get our B value, we're not simply going to take that 13%. What we want to do is we really want to figure out what is going to be left every year after that depreciation happens. So because it's decay, I'm going to subtract from 1. So let me write that up here. If it's depreciating, we're going to subtract from 1. And then notice that I converted the percent to a decimal. You're always going to want to do that. Remember, we never use percents in problems. We always convert them to decimals. Okay, cool. So then the last thing that I need in my equation is the x value, which is the time over which the situation is happening. And that's, we know what that is. That's 7 years. Cool. So now I'm going to simplify first, and then I'll be able to solve. So I'm going to simplify that grouping. 1 minus 0.13 is 0.87 to the 7th power. And then all of that I can put into my calculator. And I did this ahead of time. So it comes out to $6,752.86. So to kind of put this number into perspective, what this means is this is the value of the car after 7 years. So you can see that cars depreciate quite a lot. It started off at $17,900, and then 7 years later, it's worth like a third of what it was before. All right, so now let's go to another example. Again, there's some interesting stuff here about savings accounts and retirement income and investment growth over time. I'm not going to read through all of that, but feel free to pause if you would like to. I'm going to jump right in with annotating our problem. It tells us right away that $6,700 is placed into an account, so that is going to be our initial value for this equation. I'm going to start writing it. 6,700. All right, and then we need to know what our growth is. So in this case, it's an annual interest rate of 1.75%. Really, this should say that this is a savings account that's appreciating at a rate of 7.5 or 1.75%. But I will make that super clear that this is growth. This is money sitting in an account that's growing at 1.75% every year. And then it asks us how much is in the account after 28 years. So 28 years is our time value, and let's just double check that time does match the units in our rate. The rate is annual. Okay, so then because, oops, I didn't mean to do that. Because this is growth now and not decay, now we know that we're starting with one whole and then we're increasing every year. So again, I need to convert to a decimal. So I'm just taking that 1.75 and dividing by 100. And then I know that my x value is after 28 years. So again, a little bit of simplification first. And then I'll go ahead and type all that into my calculator. Pause here, make sure you get the same number I do. Calculate that out. When you do that, you should get $10,890. And then we're rounding to the nearest cent. So hundredths place, because there's 100 cents in a dollar, so we'll round to 2 decimal places, hundredths place. Cool. So that's an account that's not growing by very much. It's only growing 1.75% every year. That's pretty typical for a savings account. That's actually a little bit on the high end right now for a savings account. So really, if you're looking at long-term investments, you're really going to be wanting to look at investments that grow between 6 to 11% per year for something that's like long-term. Like this might be, retirement money that you're putting away in an account that you're not going to touch for a very long time. For those types of accounts, you really want to look for investments that are growing a little bit faster than 1.75%. Okay. On to the next one. Oops. Hope you didn't see that. Okay. So we're going to continue just building exponential functions and evaluating them. Here's one where a town initially has a population of 13,000. It tells us the rate of growth. It's growing just a little bit, 2.5% every year. And then it does tell us the time over which that's happening. Our units match, 5 years. The growth is occurring every year, so we can proceed. I know my starting value is 13,000. And then we are experiencing exponential growth. So I'm starting with one whole and I'm going to add that 2.5%. I do need to convert to a decimal. I was just thinking. So 2.5% divide by 100 gets 0.025. And then this is happening over 5 years. We want to know the population after 5 years. Simplify it up. And then evaluate. Go ahead and pause. Do that. See what you get. Always notice what you're rounding to, because that can sometimes make or break your answer. We want to round to a whole number here because it doesn't make sense to have like a decimal of a person. Like, we're only going to be counting whole people in this scenario. There's no half people here. Okay, one more example, and then that's it. That's the end of the video. All right, so this is something that you'll talk a lot about in physics if you go on to take more physics. This is decay that's happening over time. So often elements decay over time by emitting radiation. This element, its initial mass is 670 grams, and it is decaying, oops, I went green, decaying at a rate of 21.8% per minute. Wow, that's really fast decay. That means every minute it is decreasing 21.8%. So we're looking at a short time span here. We want to know only after 15 minutes because this decay is happening per minute. It's happening pretty quickly. Okay. Our initial value is 670 grams. That's how much of the element we're starting with. This is decay. So I'm going to start with one whole. I'm going to subtract. What is that decimal? 0.218. And then I want to know 15, every minute, at each minute this is happening, I'm multiplying that base. So I'm going to do that 15 times for 15 minutes. Just a little bit of simplification. And then it's ready to go into the calculator. Go ahead and pause. Actually, I think I'm going to put in a question here. Round to the nearest tenth. Should get 16.8 grams. All right, you did it. You made it to the end of the video. Hope you enjoyed. Have a great day.